Today we're going to be transforming quadratic functions. We're going to look at how changing the a term, which is the term in front of the x squared, and how changing the constant, which is the c term, affects the quadratic function. First, if you look at these quadratic functions that are here, they're color coordinated. If you look at the number or the coefficient in front of the x squared term and look at the width of the parabolas, that's what we're doing right now. So if you look here in the first one, it's green. The coefficient in front of the x squared term is a decimal, which is a very small number. But look at the width of the parabola. It's a very small number in front of the x squared, and yet the parabola is very wide. In the next example, we have 4 as the coefficient, which is a larger number than 2/10. But look at the width of the parabola with the red. It's narrower. The last one we have there is called the parent function, where the coefficient is just 1. Notice that it's in between the two. So how does the coefficient change the width of the parabola? The value of the a, that means the number or the coefficient in front of the x squared, determines the width of the parabola. And if you look at this, you will see that the greater, this says here, if the absolute value of a number is greater than 1, that is right here with the number 4, the graph will be narrower. So the larger the number, the narrower the width. In the second one, if the absolute value of the a term is less than 1, if it's a decimal or something small, as an example right here, you will notice that the graph will be wider. So in essence, they're opposites. The larger the number, the narrower. The smaller the coefficient, the wider. Here's another example right here. You can see 3. The yellow is 3x squared. If you look at the coefficients here, we have 3 and 2 and 1. 3 is the greatest number, but is the narrowest parabola. Then 1 is the smallest number, and yet it is the widest parabola. So you just have to kind of get into your mind how that works. Now, let's take a moment here, and I'm going to show you a website that you can go to, desmos.com. We'll come back to this. Desmos.com is that graphing website that we went to. And right here you see the x squared has been graphed. Now, if I change the coefficient in front of the x squared for a second one, I can sit here and play with this. And you could go to desmos.com and play with this too. Let's work with the coefficient here in front of the x squared term. Let's make it a number that's greater than 0. Let's make it 6. Okay, notice that this indicates black right here. I don't know if you can see it on my screen. It is narrower with the 6. If we try another one and we say y equals, and let's do a decimal, 0.05x squared, you will see that this is a very small number, small coefficient, but look how wide the parabola is. And you could go to this side and you could just play with this and plug in some different numbers. You could go crazy and type in like 50, and you can see how narrow that is with the red right there. You could do a very, very small number, 0.007. Look how wide the parabola is. So the a term, or the coefficient in front of the x squared term, determines the width of the parabola. Now if we go back to this, okay, let's look at how we're going to see. Okay, now notice that some of these are negative and some of them are positive. If you remember back to a previous lesson, the number in front of the x squared term, that negative does something for us. All it does is tell us whether the parabola is going to be up or down. It does not, let me repeat, it does not change the width of the parabola. And that's what we are looking at right here. If you go back to the slide right here, we were looking at the absolute value of the number. It doesn't matter whether it's positive or negative. The positive or negative just tells you whether the parabola is going to go up or down, but it doesn't change the width. So when you're comparing the widths, you're just looking at the absolute value of these numbers. So if you look right here, You look at the absolute value. The absolute value of -2 is just 2. The absolute value of 1/3, of course, is 1/3. And the absolute value of 4 is 4. This one would graph down, and these two would graph up. But all we care about is the absolute value of those numbers. Which one would be the narrowest? We're going to order them from narrowest to widest. To get the narrowest, we have to have the largest absolute value. So we name these functions with different letters. So the number with the largest number would be called h of x. That function had the narrowest parabola because it had the largest number. The next one would be the f of x function. Now the -2, the negative just means, of course, again, that it goes down, but the width doesn't change. And then the widest one would be the one that is less than 1, which is 1/3, or that would be a decimal of 0.3 repeating. So we're just ordering these from least or from narrowest to widest by looking at the leading coefficient and looking at the absolute value of those. In the second example, let's look at here we have -4. That is going to go down, but the absolute value is 4. We have 6, and we have a decimal, 2/10. So which one of those would be the narrowest? The one with the greatest number. So that would be g of x. So we did that one. Which one would be the next one? That would be the f of x with an absolute value of 4, and then the decimal would be the widest one. Now, let's add another number to our quadratic function. We're going to, you know that in a quadratic function we have ax squared plus bx plus c. We're not going to deal with this center term today. We looked at the first with the x squared, and this coefficient tells you how wide or narrow it's going to be. And now we're going to look at the last term, the c, the constant. And this is going to tell us something about a quadratic function as well. Okay, look, compare the coefficients in the c terms. In other words, I want you to compare the -5, and this one has no constant, so that this is 0. How does the coefficient, or how does the constant, change the position of the function? Well, if you look up there, the value of the c in the quadratic function determines the vertical translation. What does that mean? In this one right here, since there was no constant or no c term, we understand it to be 0. Look where the vertex was. It was on 0 on the y-axis. Look at this -5, and look where we cross right here is -5. This is going to tell you the y-intercept, or the vertical translation. This one was down 5 because it had a -5. It went down 5 from the parent function. So if you look right here, we have the same width because both of these have a coefficient of 1. This one has a y-intercept of 0, so that would be this one. This one says +1, so this one is going to cross the y-axis at 1, so it was translated 1 unit up. So if c is greater than 1, the graph is translated up, because when you go up on the y-axis, you are getting to larger numbers. On this one, you'll notice that the c term is translated 5 down. That means it crosses the y-axis at -5. That is a negative number, and when it's negative on the y-axis, which is a number line, you go down. So if the c is less than 0, or a negative number, the graph is going to be translated down. Positives go up, negatives go down. So now we're going to compare a graph of a function with the parent function. Now the parent function is when you simply have the coefficient 1 in front of x squared and the y-intercept is 0. So we just say f of x is x squared. That's the simplest quadratic function that you can have, and it is actually already graphed over here for you. Now let's compare this quadratic function right here. What do we know? The width. This has a coefficient of 3. Is that going to be wider than a coefficient of 1, or is it going to be narrower? The number is larger, so we know it's going to be narrower. Now, the axis of symmetry actually has to do with the term that we're not dealing with today. So the axis of symmetry is not, that is going to be how it translates to the left or right, and we're not going to be translating to the left or right today. So you're just always going to say the same. We're not dealing with that today. You're going to compare whether this one opens up or down. So if you look up here, this was a understood invisible 1. That goes, we know that it's going to graph up. This has a positive 3, so we know it's also going to graph up. So we can say they both are open up. What about the vertical translation? You look right here at the C. It's negative. Since it's a negative 4, we know that it's going to be moved. When we say translated, it's going to be moved down 4 units, which represents the negative 4. Now you're going to roughly graph this just based on the information that you know right here. We know that the vertex was down 4 units. So on our graph paper, we're just going to put the vertex down here at negative 4. And did we discover that this was going to be narrower or wider? We said narrower, so we're going to draw it. And just roughly, it doesn't have to be exact, but just show that indeed would be narrower than the parent function. So we're just doing a rough estimate here just to give you an idea of how this works. Okay, again, we're comparing this g of x function to the parent function. And again, the parent function is graphed right here. You can see it already graphed. Let's compare them. The width. This one had a coefficient of 1. This one has a coefficient of an absolute value of 1/4, which is less than 1. It's a small number, so we know the width is going to be wider. The axis of symmetry, we're not dealing with today. They're always going to be the same. We're not shifting them to the left or right today. If you look up here and compare whether they open up or down, we know that the parent function opens up. This one is negative, so we know that it is going to graph down. And the vertical translation, we look right here, we know it's going to go up 3 units because it's a plus 3. So now we're going to roughly graph it. The vertex is going to be at 3 on the y-axis. We know that in this one it's going to go down, so we know we're going to draw it down. And we know it's going to be wider, so we're just going to show it going down and being wider than the other one. We're not going to be exact, we're just showing some knowledge about how the coefficient affects the narrowest, the width of the quadratic function. Now let me show you how this is going to work in the real world by pulling up this page right here. Okay, this is practicing in the real world. Now before you start this page, you need to read and make sure you see this right up here in the top upper right hand corner. There is a quadratic function that we use based on the gravitational pull of Earth, where negative 16 t squared plus c can be used to approximate the height in feet above the ground of a falling object. This is an equation based on Earth's gravitational pull. The t stands, we're going to put that in place of the x, that stands for the time. And the c is going to be the y-intercept, which is the initial height. All we have to do is plug in numbers. So if you look over here at number 1, 2 construction workers working at different heights on a skyscraper dropped their hammers at the same time. The first one was working at a height of 400 feet. So you have a building and you have this dude up here 400 feet off the ground, and he drops his hammer. When he drops his hammer, and if you were to graph that, it would actually graph as half of a parabola because it's based on distance and time. All we're going to do is plug in these numbers though. Okay, we don't know the time yet, but we do know that the initial height was 400. So all we have to do to write that is h of t. I'm going to use t in place of x because that represents time. We know it's negative 16 t squared, and all I have to do is fill in the initial height, which is 400. So all I did was take his height, and I plugged it into c because that's what c stands for, is the initial height. Because if you have a graph, the y-axis would represent the height, and the 400 would be right here where it starts. For the other guy, he was at a height of 160 feet. So again, we have another equation, but all we do is we change the initial height to 160. So we're using this equation, and we just plugged in the initial height. Now it says to graph the two functions. Well, how do we graph them? Well, if you look at the graph, you will see that the x-axis, or the domain, is time. So we have the numbers for the t. Here, t is for time. If we plugged in these numbers for t, for time, and solved for the y, we could graph it. For example, the first one is Let's see. We know at 0 seconds when he dropped it, he was at 400 feet. So we're going to put a point up here, approximately 400. What happened after 1 second? Well, the equation was negative 16. Let's plug in 1 second because that's the next thing that we have on our graph, plus 400. We always do the exponent first. 1 squared is 1, so we have negative 16 plus 400. So basically you have 400 minus 16, which would be 384. So after 1 second, it was at 384 feet. We're going to approximate that over here on our graph. Let's see, 360, 70, 80, somewhere around there. It's hard to get it exactly on a PowerPoint. Where are we going to graph it to? Well, at 2 seconds, we're going to plug in 2 for the t. So we'd have negative 16, 2 squared plus 400. We do the exponent first. 2 squared is 4. Negative 16 times 4. And then plus 400 would be, I don't know the exact number. I'd have to do that. But as you do these, you'll notice that it's going to keep going down, 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 and down. Eventually, it's going to hit the ground. But where is it going to hit the ground? In how many seconds? So you can continue to plug in these numbers and solve the equations, get the numbers, and get the points, and figure out where they would go. Now, that brings us to question number 3. Based on the graphs you drew in the problem, how long will it take the hammer to reach the ground? If you plugged in all these numbers, at some point, it should hit the ground at 1 of those seconds. So you could look over there at the graph to figure out the answer. If you want to do it mathematically, if it hits the ground, what would the height of the hammer be at that point? 0. So all we would have to do is plug in 0 to the y, which is the same thing as the h of t. If we plug in 0 for the height, and then we have our equation that we started out with. So when he dropped it from 400 feet, when did it hit the ground? We would solve for t. First, we would have to subtract 400 from both sides of the equation. So we would have negative 400 equals negative 16t squared. Now, in order to get t squared by itself, we divide both sides by a negative 16. That is going to give us 25 equals t squared. In order to solve for t squared, we take the square root of both sides, and we see that the time would be 5 seconds. So this over here, for this first one, should have been hitting the ground at 5 seconds, and your parabola should look something like that. And you can do the same thing with the gentleman who dropped it from 160 feet. You would just replace this number right here with 160, and you would solve and see how many seconds it took for it. It may not be a whole number. It's not going to be a whole number. It's going to be a decimal. For the bottom half of the paper, use the information that we learned today. It talks about, here's the planetary gravitational pulls. We have different planets represented here. We have Pluto, we have Jupiter, we have Earth. Now, think about the widths of the parabolas. That's going to tell you something about that leading coefficient. Okay? Think about the time and see if you can use the information that you learned today to look at this graph and deduce which the correct answers would be. You can check your keys to see if you are right. And that concludes our lesson.